Hello everyone. So today we'll be talking about FMEA, failure mode and effect analysis. So the FMEA itself is a bottom-up analysis. It's inductive, and that means that we use it to identify how components can fail and what effects each failure has on the system. So we go from failure modes of specific components and we check what are the consequences on the subsystem, the system, or all the way to the asset level. And it is one of the most widely used tools in safety and reliability engineering, of course. And here, regarding the FMEA itself, it asks this component fails, so what? What are the consequences? And it's a complementary analysis actually to the FTA, the fault tree analysis, which asks the reverse question. It starts from like an undesirable event and asks, oh, this is bad thing happened, so, and then why? And we look into the combination of different events that led to that undesirable event. So they go hand in hand, FMEA, FTA, with the different levels of understanding of our systems, for instance, and it's a way actually to document and understand what are the causes and consequences regarding failures in our system. And the core structure of the FME itself is based on these 6 steps. So we start by scoping the item or the function. We just mentioned, what are the items, different levels, subsystems, components, parts, what are their functions. And then we assign failure modes actually to those elements. So there could be one component presents like several failure modes, like an open circuit, stock close, excessive output, as you can see there. Also, what are the effects of these failure modes? That's the next question that we ask, and we try to look at those and identify as much as possible, considering actually the different connections in the system. We check the local effect, we check the next level effect and effect, for instance, on a higher level. We can also look into effects and consequences in terms of safety for the users, in terms of operational, let's say, criticality, regarding also like the mission, some environmental consequences. We look to all these type of effects, and then we look into the causes of that failure mode. Those are actually the elementary causes or mechanisms that lead to the failure mode. For instance, it could be just a bit flip inside a specific circuit board that led to that, or any external factors that led to the failure mode. And we check also how this failure mode is detected. Is it something that goes perceived actually by like an operator next to the machine or the system that is working, or is it undetected in that sense? And finally, we look into the controls that exist. What are the control measures that we have in order to prevent the failure mode to happen? So these 6 steps are mainly, identified and organized in a sort of a table, and this table is used to summarize all that information and keep it and maintain it as we move on in the project. There are several types of FMEAs depending on the applications. We start with design FMEA. This is the most used type of FMEA, let's say. It catches design weaknesses and things that slips through the cracks at the early stage of design. And this is done mainly, before we even start, putting the hardware and assigning these functions to hardware themselves. So we look at the failure modes like from a functional, let's say, perspective. And then process FMEA that considers the manufacturing and assembly failure modes at that level. Things that could, lead to defects in the system that are based actually on the, for instance, some elementary causes happening during assembly, like a loose screw or an inadequate type of assembly, for instance. Those elements we catch them in the process FMEA. And there's more abstract level FMEA, system FMEA, which looks more into the interactions between subsystems, and it looks into the failures regarding integration and interfaces between different systems or components. So mainly in safety engineering, design FMEA is the most relevant, as we said, but we have those other types of FMEAs. So whatever you find yourself asking those 6 questions that we talked about, you're doing an FMEA. For instance, if you're doing also an RCM, reliability centered maintenance, the first part of it is actually FMEA. And then in the mitigation or in the, let's say, the controls, you can develop your maintenance plans to bring the system back. But that's something we're going to cover in a future video. And now we're just like touching the RPN. As you can see here, FMEA per se, there's another topic, of course, the FMEA, which adds and extends the FMEA with criticality. But here we're talking about the risk priority number. That's the RPN versus safety-driven classification that we find mostly in the different types of standards. So the RPN itself is the multiplication of severity, occurrence, and detection. If you place on each one of these variables a number from 1 to 10, you will end up with an interval that goes from 1 until 1000 actually to classify a specific failure mode. We will see actually that this is also limited, but in general, the way you read this is the higher RPN means the higher priority to address. And it is used actually to classify and also prioritize the engineering efforts in order to look at the most critical parts of the system and address those failure modes early, and give them the attention, the effort they need. But there, RPN is not a safety metric by itself. So a very frequent minor issues can outrank a rare but catastrophic one. You can see it from, the different variables in the equation of RPN. They're not weighted. So you can have something that has high severity, but let's say it doesn't occur that much. So we will not be actually looking into it as a critical one. And it's easily detected, for instance. But in general, in safety-driven context, when you have safety-critical, mission-critical systems, for instance, here with automotive ISO 26262, or in general for the EEPE systems, functional safety, like the IEC 51508, 61508. Here for the EN 5126, we're talking about railway, for instance. So the FMEA here is used in different aspects. So the effects themselves are mapped to hazardous event that describes actually a specific accident. So it describes what is the hazard, what is the potential source of risk, and it links it actually to the potential existence of a human, for example, in the radius of that source of risk. And then we use actually other metrics to classify those hazardous events. For instance, the output of an FMEA from an elementary level would feed into these hazard analysis and risk assessments, or the safety cases if we're talking a railway. And the focus there would shift from prioritizing fixes to demonstrate that all hazardous failure modes are addressed in one way. Actually, they're identified and then addressed with the adequate mitigations. And then we look more into specific domains. As I mentioned, automotive there, the output of the FMEA would feed into the HARA, and then would assign an automotive safety integrity level decomposition, and use it also to produce some diagnostic coverage as we move on with the hardware. For railway, it's used as an evidence in the safety case along FDA. Also in machinery with the ISO 12100, it informs the risk estimation step. There we consider hazard identification, and then we need to do a risk estimation there. So the FMEA itself helps there, and in general the IEC 61508, it's a recommended techniques for the hazard analysis in general and the reliability analysis. As we mentioned earlier, there are some limitations for RPN specifically, but in general for FMEA, one failure at a time. That's how we analyze the failures inside FMEA. And this is inherently misses, the combinations of failures. So if two simultaneous faults happens, you will not be able actually to combine them or look into them in that sense. Also common cause failures. So when you have one event that disables multiple channels or influences multiple channels, that also goes under the radar. You cannot easily detect it actually using FMEA, since it's in its tabular format as it is. It's not very, I'd say, optimized for that. And also cascading sequences. And that's where actually FTA comes into picture, because it could handle combinations via AND gate, OR gates, all different logical gates like XOR and KRFN. And it adds, also we would look into the FMEK itself, where we add criticality ranking to prioritize the worst combinations. And for those, there are other standards also for specific type of applications. For example, the military standard the 1629 A, which is the FMEA standard for military assets. So as we mentioned, in practice, the FMEA and FTA would go hand in hand. They would be used together. FMEA goes like a bottom-up approach. It goes like across all components, and then FTA, top-down approach, deductive approach, goes deep into the most critical top events. And in other videos, we will be discussing, FMEA, FTA, HARA, ISO 26262. This is something I see a lot of people interested in. Mainly with the new, let's say, usage of these sophisticated components in automotive industry, mainly, ADAS applications. EN 50126, that's for railway. Railway is a well-established domain. Let's say ramps in general in railway is well-established, and it covers these different analysis and methodologies. And finally, in general, we're talking about ramps engineering in this channel, and FMEA itself is the primary tool for reliability analysis and also for safety analysis. At some point, we will look into it. So it's a really handy tool to have in your tool set. So that's it for this video, and I'll talk to you in the next video.